All right, so welcome everybody to our monthly Zoom seminar. So it's a pleasure to have today Pierrick Bousseau, who will tell us about the KSBA moduli spaces of log Calabi-Yau surfaces. Please go ahead.
All right, so thank you very much for the invitation to speak at this online talk. So in the plan of my talk, I will first recall a few things about KSBA moduli spaces of stable varieties. And in this talk, everything will be about the field of complex numbers. And then I will review a non-story, essentially due to Valery Alexeev 20 years ago, which is about the description of particular examples of such moduli spaces in the context of toric geometry. And I will point out the relevance of mirror symmetry for this non-toric story. And then the main result of this talk will be a non-toric extension of the non-toric story, which is about a moduli spaces of a particular class of log Calabi-Yau varieties. And our main result will be in dimension 2 for log Calabi-Yau surfaces, and will be a statement of the form which is in the box on the slide. We'll prove that some KSBA moduli space of particular stable log Calabi-Yau surfaces are essentially toric varieties. More precisely, they will be image of some finite surjective map from a toric variety. And this thing will be establish a conjecture due to Keel, which conjecture that there should be such result for log Calabi-Yau varieties in any dimension. The appropriate moduli space should form a toric variety up to a finite map. And what should be mentioned, what is maybe remarkable about this type of result, is that there is no toric assumption in this statement. The assumption involves a particular class of log Calabi-Yau surfaces or log Calabi-Yau varieties, conjectural in general. There is no toric assumption, but somehow the output is telling us there is something toric about the moduli space. So there will be something combinatorial as the output, whereas it's unclear there is anything combinatorial in the input of the result. And so the main result I will be talking about in this talk is joint work with Alexeev and Julia Argus, and is contained in some paper which is on arXiv since 1 year. Okay, so let me start at the very beginning by recalling some known things.
Sorry, Pierrick, I
So
think I can just see your
yes,
first slide. Okay, is it okay? Did you start
so,
actually? It should have been.
yeah. So do you see? So what slide do you see? So
Just
actually, I just see now. I see your string sharing is paused. I don't know if there's some technical. So do you see the first? Do
I
you see
just
the
see
title slide?
the title slide. That's right.
And here, do you see a new slide or still the title slide?
No.
Okay, so there is a problem. Um, should I try stop and try again sharing? Stop share. And let me um, share again. Share.
Okay. No, it's okay.
Yeah, and now, so here's the title and here's the next slide.
Yep.
Okay, yeah. So yeah, we're just using this first slide, which only contains the plan of the talk. I was just describing. There's not much to miss there. Okay, so let me start by reviewing very classical moduli spaces, the moduli spaces of stable curves. So if you fix GNN non-negative integers, we have MGN bar, the Dölling-Mumford moduli space of point-in stable curves, C P1 to Pn, where C is a reduced curve with arithmetic GSG without nodal singularities. P1, Pn are distinct smooth points, and these pairs of a curve with mark point is stable in the sense its automorphism group is finite, or equivalently the canonical divisor on the curve plus the sum of the mark point is ample. And this moduli space is one of the nicest moduli space in algebraic geometry. It's a proper Dölling-Mumford stack of dimension 3G minus 3 plus n. And it's a nice compactification of the moduli space of smooth curves with distinct mark points. And KSBA moduli spaces are a generalization for higher dimensional varieties. So KSB is for a Kollár-Shepherd-Barron, which introduced the notions in the notion for in dimension 2 in the 80s. It was further developed by Alexeev in the case of pairs. And so a stable pair is a pair. So before we had curve with mark point. In higher dimension, we have a variety Y, projective variety, with a divisor. So B will be a Q divisor, a divisor with possibly rational coefficients between 0 and 1. And there are two conditions. So as for curves, there is a condition of singularities. For curves, you want it to curve to be at most nodal and the point to be smooth. And here there is a higher dimensional version of this condition. You want the pair YB to have a so-called semi-log canonicals or LCC singularities, which is a natural notion coming out from the minimal model program. And there is in addition a stability condition, which is again some ampleness condition. You want the canonical divisor KY plus the divisor B to be a Q-Cartier divisor. So up to a multiple, it's a line bundle, and you want this line bundle to be ample. And so due to the work of many people, so starting with Kollár-Shepherd-Barron, Alexeev in dimension 2, and then by many people, I guess including many people in this collaboration, there is by now a complete theory of these Moduli spaces. And in any dimension, it's known that these Moduli spaces are really nice in the sense that the connected components are proper Deligne-Mumford stack. So you have nice Moduli spaces of these stable pairs. But unlike the case of curves, they are generally not irreducible and not smooth. And so describing explicitly the geometry of these Moduli spaces for higher dimensional varieties is often a not so easy task. So I will first describe a particular example of these Moduli spaces, which can be viewed as a particular example of this general theory of KSBA stable pairs in a very concrete setup, which is a setup of toric varieties, where everything can be described concretely because it can be essentially reduced to some combinatorics. So torically, so let me fix some combinatorics. Let me fix P some lattice polytope in Rn. Then it's known that such lattice polytope naturally defined a polarized projective toric variety. So how do you get this projective variety? Starting from the polytope P, you can construct what I denote by Cp, which is a cone of a P. You view this polytope in Rn as being contained inside Rn plus 1, where the last coordinate is 1. And then you take the cone over this polytope, you'll produce an n plus 1 dimensional cone. And then you can look at the set of integral points inside this cone and look at the corresponding, it will be a monoid, and you can look at the corresponding monoid algebra. So concretely, you get one monomial for each integral point in this cone. You get a graded ring, and you take the proj of this graded ring, you get a projective toric variety. So I will denote by D the union of toric divisors, which is an anti-canonical divisor. And I will denote by L the natural ample line bundle coming from this proj construction. And by construction, the space of sections of this line bundle can be identified with a space of monomials indexed by these points inside, by the lattice points inside the polytope. So here I draw some pictures. On the left, I have these lattice triangles of size 3. And the corresponding porous projective variety is simply P2 with line bundle of 3. And the sections of 3, they are simply the natural basis of monomials in XYZ of degree 3, which are in one-to-one correspondence with integral points in this triangle. And on the left, I wrote a different picture, which is obtained from the right by forgetting. So on the left, you should only look at the pink square. So it's obtained from the right triangle by cutting some 3 white triangles, which geometrically has to do with some blow-ups. You do some blow-ups of the previous examples, and you get this pink square. And the variety attached with this pink square is a singular degree 4 Del Pezzo surface with 4 A1 singularities, and the corresponding line bundle happens to be anti-canonical line bundle in this example. Okay, so by some relatively standard toric geometry, if you start with a polytope P, you produce a toric variety Y. It has a union of toric divisor D, and there is an ample line bundle L on it. And now I will look at particular pairs, which are pairs of the following form. So I will consider my toric variety Y, and I will look at some divisor of the form D, so the union of the toric divisors, plus epsilon C, where C is a divisor in the linear system of the ample line bundle L. And here I put some epsilon in front of this divisor. Epsilon is a rational number, positive rational number, very small enough. And one can show that when epsilon is small enough for this kind of pair, the notion of being semi-log canonical actually drastically simplify and reduces to the condition that this divisor C is torically transverse in Y, which means that it does not intersect the zero-dimensional strata of the divisor D. So here on this picture, this square is supposed to represent a toric surface, YD. So the side of the square are the toric divisors. I have 4 toric divisors in this example. And in addition, I have this divisor C in red, which is in the linear system of this ample line bundle L. And I consider the pair consisting of this toric surface with a toric boundary in black, union the toric divisor in red. And the divisor C in red has a coefficient epsilon, and when epsilon is small enough for this pair to be semi-log canonical, it's enough for this red curve to avoid the zero-dimensional strata of the black square. And so you can see that by construction, if I consider such a pair, YD plus epsilon C, then ky plus the divisor will be ky plus d, which is 0 because d is anti-canonical, plus epsilon c. So the total log canonical bundle is epsilon c, which is indeed ample. And so like that, I produce a lot of stable pairs. And then I can consider what I will denote by MYDL, the closure in the Moduli space of all stable pairs of this form. So the claim is that if I have my toric variety and I pick a divisor C which avoids the zero-dimensional strata, I get an example of a stable pair. But of course, the Moduli space of such a pair is not proper because typically my divisor C at some point will intersect a zero-dimensional strata. At this point, this pair will no longer be stable. And so something interesting will happen in the full Moduli space of stable pairs. In the same way that if you look at curves, and if two mark points collide, or if a mark points go to a node, something interesting will happen to the curve. Typically, the curve will break into more irreducible components. And here, something similar will happen. So in this Moduli space MYDL, the general element looks like this irreducible toric surface with this divisor in it. And when we take the closure in the Moduli space of stable pairs, in the boundary, the toric variety will break into pieces, and the divisor will also break into pieces. And understanding the Moduli space has to do with understanding what happens at this on the boundary. Okay, so we have this Moduli space, MYDL, and you have this theorem due to Alexeev around 2002, essentially describing completely this Moduli space. The statement is that its normalization is itself a toric variety, and it's a toric variety, so it should have a fan. And this fan is a so-called secondary fan of the momentum polytope P we used to define the polarized pair YDL. And so this secondary fan, it's a combinatorial construction. You can apply starting from a starting fan of our starting variety to produce a new fan, which will be the fan describing this Moduli space. And this combinatorial construction of a secondary fan is originally due to a Gelfand-Kapranoff-Zelevinsky. So in this theorem, you have some toric input, some lattice polytope. Out of this input, we could come some Moduli space, and somehow this Moduli space itself happens to be toric, to have a toric combinatorial description. And because there is a toric input, the fact there is a toric output is maybe not so surprising. And let me try to explain how this toric output is coming about. So why should you expect in this example the Moduli space to be a toric variety? So first of all, here is some discussion of what the secondary fan is. So I will not recall the full combinatorial description, but essentially it's a fan whose encodes the combinatorics of polyhedral decomposition of the original polytope P. In particular, the maximal cones of this secondary fan are in one-to-one correspondence with the so-called regular triangulations of our polytope P. So here is some example. So I take this square polytope P, which was in pink before. Let me come back here. So here on the right, that's this pink lattice polytope. And you can ask what are the possible triangulations of this polytope. And here there is like 3 triangulations which are drawn on this picture. You want these triangulations to be so-called regular, meaning these triangles should be the domains of linearity of a piecewise linear function on your polytope. And so in this example, there are essentially 3 such triangulations. And the secondary fan is drawn on this picture. It will be a 2-dimensional fan represented in blue, so delimiting 3 2-dimensional cones. And so in this example, you see that this fan is a fan of the projective plane. So in this particular example, the KSBA Moduli space happens to be 2-dimensional and happens to be simply a P2. And so what I want to explain is now why you might expect in this situation the Moduli space to be toric, and what does this picture of triangulations has to do geometrically with describing the boundary of the Moduli space. So first of all, so if the Moduli space is supposed to be toric, in particular, it should contain a preferred torus. And so you might ask, why is there a preferred torus inside our Moduli space? So here, our Moduli space is parametrizing this toric pair, YD, and then we add to it epsilon times C, the divisor in the linear system. And in this story, the pair YD is essentially rigid. So the toric variety with this divisor does not have non-trivial deformations. And so all the moduli come from moving the divisor inside the linear system. And so how do you parameterize your divisor in the linear system? You just write the equations given by sections of the line bundle. And by the toric construction, sections of the line bundle L have a natural basis given by monomial z to the p indexed by integral point p inside the polytope capital P. So concretely, it's like this section of this line bundle, if you restrict it to the torus inside the toric variety, it will simply become a Laurent polynomial. And this coefficient AP are the coefficients of this Laurent polynomial. So here's something which will be important for later. There is this fact that for ample line bundles on toric varieties, space of sections have a preferred basis given by these monomials, these toric monomials. Which means that inside the linear system, there is a preferred torus, which is a torus consisting of equations or polynomials whose coefficients are all non-zero. So there is this torus inside the linear system. And it's elementary to check that if you have such polynomial with coefficients are all non-zero, then the corresponding divisor will be automatically torically transverse. It will automatically avoid the 0-dimensional strata of the toric variety. Which means that the pairs of this form will be automatically stable, and so there will be a torus inside your Moduli space, a preferred torus. Okay. So it's a good start to understand why it's toric, and then to go beyond, so the Moduli space is some kind of compactification of this torus, and we need to understand what happens at the boundary. And the point is that this secondary fan, which gives a particular compactification of this torus, in terms of this combinatorics of triangulation, is encoding the combinatorics of degenerations of our stable pair. So the way you should read these triangulations is as giving you a picture of how your toric variety behaves at the boundary of the Moduli space. So if you look at the picture at the bottom, I'll start with my polygon P, which is the red square. And you should think of this red square as some kind of picture of a corresponding toric surface, which is irreducible with 4 irreducible toric divisor components. And when you go to the boundary of the KSBA Moduli space, sometimes this square will break into 2 triangles. And you should interpret this picture as saying that the surface will become reducible, it will break into two toric varieties, having themselves toric polygons given by the two triangles. So these various triangles and or polyhedral decompositions describe combinatorially how is your toric varieties breaking at the boundary of the Moduli space, and it's breaking into a union of smaller toric varieties. And correspondingly, the divisor C, which is represented in green in this picture, in the limit breaks into various divisors into the various components of the various toric irreducible components. So in this toric situation, essentially everything is understood. Things are as nice as possible. The Moduli space is toric. And there is a clear understanding of why it is the case, because there is this preferred basis of monomial, so you have this preferred torus. And the full boundary is entirely described combinatorially by this combinatorics of polyhedral decomposition. And the resulting fan, which describes the Moduli space, is this secondary fan, which is a completely combinatorial object. So our goal later, in a few minutes, will be to go beyond toric examples, beyond toric pairs. And before doing that, I would like to reformulate the toric situation in a way which would be useful to understand non-toric situations. And the claim is that these previous results, the fact that these KSBA Moduli spaces of toric pairs, of stable pairs of this form YD plus epsilon C, the fact that it's toric, can be understood in a kind of dual way in terms of something called mirror symmetry. And so mirror symmetry is often stated in terms, it's supposed to be something about Calabi-Yau varieties. It's supposed to be a duality between Calabi-Yau varieties. So I need to explain that what we've been talking about until now, this pair YD plus epsilon C, how you can use them to cook up a Calabi-Yau variety of one more dimension. And it's a very simple construction. And here, just for concreteness, I wrote down what happens if I start with a toric surface and YD, and I look at the line bundle on it. And the sections of this line bundle correspond to some Laurent polynomial whose Newton polytope is given by this polygon P. So by some Laurent polynomial f of xy, whose Newton polytope is a polytope P. So out of this data, I can cook up what I will denote by Z inside C2 times C star squared, where on C2 I have coordinate UV and on C star squared I coordinate XY. I can look at the affine hypersurface of equation UV equal f of XY. So Z is a non-compact threefold, and you can check that it is Calabi-Yau. It has trivial canonical line bundle. And here's a picture of what Z looks like. So you can project on the XY coordinates. So there is an obvious map from Z to C star squared. And inside C star squared, you have the curve C0 defined by the vanishing locus f equal to 0 of our Laurent polynomial f defining our divisor C. And so if you look at the fiber of this map Z to C star squared, if you look at the point away from these curves, the fiber will be UV equal a non-zero constant. So this thing will be isomorphic to a copy of C star. But if you look at the point on this divisor, the equation of the fiber will be UV equal to 0. So it will be the union of two lines, two affine lines. So another way to say it is that Z is some bundle in affine conic curve over C star squared, which is exactly degenerate over this divisor C in C star squared. So I'm simply encoding the data of the pair C star squared with a divisor into a geometry which has one more dimension, and I encode this divisor as being some kind of degeneracy locus of this affine conic bundle over it. And the point is that, why am I doing that? I'm essentially doing that for a motivational purpose, to explain that instead of considering pairs as before, YD plus epsilon C, I might as well consider this geometry Z, which is Calabi-Yau. And now there is no longer any pair, or there is no longer any divisor. It's just some honest, non-compact Calabi-Yau. And what I was doing before, which was looking at the moduli space of stable pairs, like moving this divisor C inside the linear system, you can interpret that as changing the algebraic or complex structure on this Calabi-Yau Z, because you just change the equation of Z. And in particular, it means that the KSBA moduli space you care about, MYDL, you can interpret it as some kind of compactification or some kind of moduli space of complex structures on this non-compact Calabi-Yau threefold Z. So because it's non-compact, it's maybe a bit tricky to really make sense of what do I really mean by the moduli space of complex structure on this variety. But definitely on the open part of this moduli space, I have a kind of universal family of Z. And so I would like to think of this 1DL as some kind of precise version, and like actually precise version of a compactification of a moduli space of complex structure on this Calabi-Yau. So which means that our original problem, which seems to be about pairs, actually has to do with moduli of Calabi-Yaus, and then you can believe that mirror symmetry should be relevant. So in general, mirror symmetry will predict that given some Calabi-Yau, there should be a mirror Calabi-Yau. And if you want to understand the moduli of complex structures or algebraic structure on the original Calabi-Yau, it should be related to a moduli space of symplectic or careless structure on the mirror. And in general, for general Calabi-Yau, it may be difficult to make sense of mirror symmetry. But in the toric situation, mirror symmetry reduces to a completely explicit combinatorial duality. So I will explain what is the mirror of the toric geometry we have been considering until now. So until now, we have been looking at some, let's say, it works in any dimension, but to fix the ID to a toric surface YD with an ample line bundle L on it, which is determined by data of a toric polytope P. And I want to cook up some mirror geometry. And so what is this mirror geometry? It will be purely combinatorics, and I will still start with my polygon P. So in this example, I took P to be this square I was using before. And previously, I was using the P as defining a momentum polytope for my toric variety. And now I want to do a dual operation. I want to use this P to construct a fan of a toric variety. And the way to do that, I simply consider the cone over this polytope. I produce some integral rational cone, and I denote by x bar the toric variety whose fan is given by this cone. And because this cone is really the cone over some polytope at height 1, there is a natural height projection giving a map to positive real numbers, which is a fan of A1. So actually, this x bar comes with a natural toric morphism to A1, to the affine line. And so this x bar is simply an affine toric variety because I have a single cone. So it's typically very singular. It's a singular toric variety. So you can check it's the Gorenstein canonical singularity. And what we will really be interested in are possible resolutions of these canonical singularities, in particular Crepont resolutions. And these particular Crepont resolutions are encoded into the choices of polyhedral decompositions or triangulations of our original polytope P. So here on this picture, I choose a triangulation into this red triangle. If I take the cone over it, I'm adding a ray to the picture. So I'm doing a blow-up of the original singular toric geometry, and I produce something which is smooth in this example. In this example, what I produce X is a total space of the canonical line bundle over P1 times P1. And X bar is a canonical singularity obtained when I contract the zero section P1 times P1 to a point. Okay, so here we should not be confused. So previously I was using the polytope to construct a polarized toric variety YDL. And the polyhedral decomposition of the polytope has to do with degenerations of this YDL. Now I am using the same combinatorial input in a dual way. I use a polytope to cook up a fan. Using this fan, I cook up a singular toric geometry X bar. And then the polyhedral decomposition of the polytope now have as an interpretation as describing the birational geometry of resolutions of this singularity. So on the original side, the decomposition has to do with complex degeneration moduli of the pairs YDL. Whereas on the new side, they have to do with birational geometry of resolutions, or if you want a moduli space of Keller structures on resolutions. And this thing should be viewed as an example of mirror symmetry. And here, from the mirror side, involving birational resolutions, like triple resolutions of our singular toric varieties, the secondary fan has a natural interpretation as being essentially the Mori fan or relative Mori fan of the geometry. So it's a general fact of birational geometry that we'll use afterwards that if you consider a triple resolution of a canonical singularity, then such morphism relatively it's a Mori dream space. In particular, there will be finitely many Q factorial birational models. The Neff cones of these birational models will be rational polyhedral. And if you put them all together appropriately, they will define a nice fan called the Mori fan of X. So here on this picture, okay, sorry. So here on this picture, I have X1, X2, X3, X4, which are like 4 chrépant resolutions of X bar, and I've put the Neff cones together. And general, these Neff cones only do not cover the full space, but you can always add some bogus cones, so-called bogus cones in the terminology of Keel, to produce a complete toric fan. And the claim is that in the toric geometry, in the toric setup I've been describing, the fan you get that way is exactly the secondary fan. So in other words, the secondary fan, which describe the KSBA moduli space, which describe something about moduli space of algebraic varieties, this fan has a mirror interpretation as describing the birational geometries built from Neff cones of resolutions of a mirror geometry. And so this thing will be particularly important. So I will now switch to a non-toric situation. And the point will be that in the non-toric situation, I will not have a direct combinatorial understanding of the degenerations we care about, like the KSBA moduli space we'll try to describe will be somehow mysterious. But if you believe in mirror symmetry, there should be a corresponding mirror story. And on the mirror story, there should still be some chrépant resolution of a canonical singularity, which will no longer be toric. But the point is that there will still be a fan given by the birational geometry of the mirror. And this fan will be the fan appearing in the main statement, in the main theorem of this talk. So if you want the kind of general logic is that in the main statement of today's talk, the statement will be some moduli space is toric. So there should be a fan coming from somewhere. And where this fan will come from, the fan will come from birational geometry. It will come from a union of Neff cones, a Mori fan, but of a mirror geometry. So let me go to the precise non-toric setup I will be considering. So I will be considering a non-toric setup which will be in dimension 2. So you could phrase the problem or conjecture in any dimension, but our main result will be in dimension 2. So from now on, I'll limit myself to this case. I will start with YDL, a polarized log Calabi-Yau surface. So Y is a projective surface, and D in Y is a reduced anti-canonical divisor. And I assume that this pair is log canonical. So for example, you could assume Y is smooth and D is normal crossing divisor. and I fix L ample line bundle on Y. And I will make the extra assumption that this pair YD is maximal, meaning that my anti-canonical divisor D is non-empty and contains a zero-dimensional stratum. It's like singular. So a typical example of that is that if you take Y a projective toric surface, D is a toric boundary, and L a ample line bundle, you will get examples of such a pair. But the point is that the class of such geometry is larger than the class of toric surfaces. So maybe I should make this maybe obvious remark. So here I start in dimension 2, because in dimension 1, if I do the kind of obvious analogous definition, the only example of a maximal log Calabi-Yau pair will be P1 with 2 points and will be automatically toric. So in dimension 1, this class of maximal log Calabi-Yau surface coincide with the class of toric pairs. So starting from dimension 2, the class of these maximal log Calabi-Yau surfaces is bigger than the class of toric surfaces. And here are some examples of non-toric pairs. You could start with something toric, for example, P2 with its toric boundary. And then if you take a point P on the toric boundary, which is not one of the zero-dimensional strata, like a smooth point of the boundary divisor, and if you blow up this point, then you get a new surface, and you created an exceptional divisor. And I take for new divisor D the strict transform of the toric boundary in P2. And by the way, the canonical line bundle transform under blobs, since D is still anti-canonical, so this new pair P2 blob in one point with this particular divisor D is a log Calabi-Yau pair. but it's not a toric pair. In particular, the complement of the divisor is no longer isomorphic to C star squared, but it's isomorphic to a different non-compact surface. Another way to produce a non-toric example, you could start with P2 again, and again start with a toric boundary, which is a union of 3 lines. And you can make a non-toric operation, which is to smooth one of the corners of this triangle, which means you replace 2 of the lines by a smooth conic. So on P2, you consider the anti-canonical divisor consisting of a line, union, a conic. And so this thing will be, again, a non-toric log Calabi-Yau pair. So even if P2 itself, you might say it's a toric variety, the pair is non-toric. So, and if you do, so using these two constructions, you can construct infinitely examples. For example, in the previous construction, you can do as many blobs as you want in the boundary of P2, so you get infinitely non-toric examples. Still, there is something, some kind of classification which would be useful later and which is specific in dimension 2, which is not true in higher dimension. So there is a result of Grossack and Keel, which is a simple consequence of birational geometry of surfaces, saying that these log Calabi-Yau surfaces always admit toric models, meaning that you can always obtain them starting with a toric pair, and then you make a number of toric blow-ups, either at the toric points. So it can be obtained from a toric surface by some number of blow-ups of points on the boundary, toric boundary, and then the possible toric blow-up and toric blow-down. So for example, this pair P2 with a line and a conic is not presented obviously as a blow-up of something else, and it's not a blow-up of something else. But the claim is that it can be related by some blow-up and blow-down to a toric pair, where the class of blow-up and blow-down is kind of constrained. So here the moduli space we'll be considering, so it's the exact analog of what we're considering in the previous situation. Where this log Calabi-Yau pair YD, and we'll pick a ample line bundle L on Y, and we look at stable pairs of the form Y, D plus epsilon C, where C is a divisor in the linear system of this line bundle L, and where epsilon is small enough. So again, by construction, because YD is log Calabi-Yau, KY plus D is 0, so KY plus D plus epsilon C is ample. And in addition, this pair will be semi-log-canonical as long as C does not contain a zero-dimensional strata of D. And now we define a moduli space MYDL as a closure in the moduli space of all possible KSBA stable pairs of the stable pairs of this form. So again, the general element in this moduli space will be this irreducible surface Y with this anti-canonical divisor D, this ampole divisor C, avoiding the zero-dimensional strata of D. And when we go to the boundary of the moduli space, something interesting will happen. Y will typically break into irreducible components, and it's maybe not so clear what happens. And the main result of this talk, of this joint work with Valer Alexeev and Ilya Argus, is that this moduli space of polarized log Calabi-Yau surfaces is essentially a toric variety. So it's a toric variety up to a finite map. So the precise statement is that there exists a projective toric variety with a finite surjective map to our moduli space. So actually in the toric situation, you can just take the normalization and you get a normal toric variety. Here it's not enough to take the normalization, you might need to take a finite map. But if you forget this finite map as being some kind of technical details, the statement is roughly the moduli space is of toric nature. And this establishes a conjecture of Keel, which conjectures that the same should be true for these polarized maximal log Calabi-Yau varieties in any dimension. And so what is remarkable about this conjecture and this result is that in this statement there is no toric assumption. Okay, so we look about log Calabi-Yau surfaces, which in general are not toric, but still the moduli space is, at the end of the day, toric. So in the entirely toric situation, it was not so surprising that starting with something toric, starting with a fan of a polycon, after doing some combinatorial construction, you could construct something like the secondary fan, which would be a combinatorial description of the moduli space. But here, because we don't have an obvious combinatorial description of the starting objects, the combinatorial description of the moduli space should come from somewhere else. And it will come, as advertised before, it will come from mirror symmetry. So here is a general strategy of the proof of this result. So on the left, we're considering these pairs YD, log Calabi-Yau surface, and I have this L, this ampole line bundle, and we consider these stable pairs of the form YD plus epsilon C. And we're interested in the KSBA stable compactification of these pairs. And in particular, we like to establish that the moduli space is essentially toric. So in particular, we need to cook up a fan, which would be like a candidate fan for a toric description of the moduli space. And because we are not in a toric situation, we don't know how to give a direct combinatorial or geometric description of this fan. Instead, we'll go through a mirror symmetry. So the main step, so in this strategy, the main goal will be to find a mirror geometry. And this mirror geometry, it is what is written on the right. It will be X bar, which will be some canonical threefold singularity. So X bar, you should think about it as being some affine variety of dimension 3 with a canonical Gornstein singularity, and which is itself a total space of a one-parameter family of surfaces. This X bar has a natural map to some one-parameter formal disk. And we'll care about the birational geometry of Crepont resolutions of these canonical singularity X bar, what I will denote by X over X bar. So in the fully toric situation, I explained how to cook up the mirror, simply starting from this polytope P and doing some combinatorics. But here, because we start in a non-toric situation, to construct the mirror, we'll need to do some non-trivial work. And it will be the main content of our work. So we do what we call the semi-stable mirror construction. We'll explain what the mirror should be in this example. And then once you have this mirror, we have these Crepont resolutions of this canonical singularity. And then by general birational geometry, there will be a Mori fan. There will be the fan made of nth cones of Crepont resolution. And this fan will be the candidate fan to describe the Moduli space we care about. But of course, there is some work to do. Why is this candidate fan the right fan? So essentially what we need to do is to identify the toric variety whose fan is given by this Mori fan with the Moduli space we care about. And so concretely, what we need to do is to produce some universal family of pairs over this toric variety. Once we have this universal family by universal property of the Moduli space, you'll get a map to the Moduli space. And then we'll prove ultimately that this map is finite and surjective. And to construct this universal family, we'll essentially apply mirror symmetry again to come back to the original geometry we care about. So you should view this full story as an example of maybe double mirror symmetry. We care about something which is maybe in mirror symmetry language is called the B side, Moduli space of varieties, Moduli space of complex structures. And you want to prove something on this side, and the way to do it will be first to find the mirror. And then on the mirror, we'll work on the A side, so we'll work with birational geometry, and as we'll see in one moment, ultimately curve counting, Gromov-Witten type invariance. And then we'll use that to come back to the original side we care about. So I would just say a few words about each of these steps. So how do we cook up a mirror? So instead of constructing the canonical threefold singularity X bar, which would be difficult to do directly, instead we'll actually cook up a Kerr-Point resolution X. And this Kerr-Point resolution X is a kind of one parameter family of surfaces. And what we'll do is to first construct a central fiber X0, a normal crossing central fiber X0, and then produce a smoothing of this normal crossing central fiber. And how do we construct this normal crossing surface X0? So I will not give all details. Let me just say that we use the fact that the log Calabi-Yau pair we care about, YDL, admits a toric model. It's related by some birational transformation to a toric pair. And for a toric pair, we know how to produce a mirror by some toric geometry. And essentially, the way you produce a mirror X0 to the non-toric YDL is by a non-toric deformation of the toric mirror. So I will skip some steps. So here there is some relatively elementary deformation theory going on. We first cook up a normal crossing surface, which is a union of toric pieces. And then you make some non-toric deformation of some of these toric pieces. And the most basic building block of this deformation is actually very simple. Some of these singular toric surfaces have Val quotient singularities, so the simplest type of T singularities, which admit some Q-Gorenstein smoothing. And we apply this smoothing as some kind of local non-toric deformation. So essentially, we run some deformation theory to cook up some normal crossing surface X0. And once you have this normal crossing X0, we show that there is a formal smoothing of this X0 into a formal family X. And this X will be like formally smooth. It will be like a semi-stable degeneration. X0 will be reduced normal crossing divisor into this formal scheme. It will be quasi-projective. It will have trivial canonical class. So this X, you should really think as being some kind of non-compact Calabi-Yau threefold. And we prove that essentially we can, inside this X, we can contract essentially everything compact inside X. There exists a contraction X to X bar, where X bar is affine with canonical singularity, so that X to X bar is a projective Kerr-Point resolution. And the way to go from X0 to X use some log smooth deformation theory. So actually this kind of arguments has been done a long time ago by Friedman in the study of normal crossing degenerations of K3 surfaces. And what we establish here is some kind of analog to this result. The main difference being that X0 is non-compact. It has non-compact components. And so one needs to adjust for this non-compactness in the deformation theory argument. So I skipped a lot of details, but the main point is that using the fact that the original geometry is related by birational geometry to something toric, the mirror will be related to something we know, something toric, by some non-toric deformation. So it is how we construct our mirror, x over x bar. And once we have our mirror, then we have this fan, because x over x bar is a Murray dream space. So you get this collection of Neff cones, and so we get a fan, and this fan is our candidate fan to describe the original KSBA moduli space. And to show that this fan is a correct fan, we need to construct a universal family over the toric variety with fan given by the Murray fan. And to do that, we start with this geometry x over x bar we just constructed, and we'll apply to it a mirror construction, which is due to Gross and Siebert, and which is a very general construction which takes as input some semi-stable degeneration of Calabi-Yau varieties. And out of it will produce a mirror, or more precisely a mirror family. And this mirror family will be obtained as a product of an explicit graded ring. And this graded ring as a module is completely explicit. So first of all, it's a module over what I denote by C double bracket any x. So any x is a cone of curves in x. And C bracket any x is a corresponding monoid algebra. And so if I take spec of C of the cone of curve, I get the affine toric variety whose fan is a Neff cone, because the cone of curve is dual to the Neff cone. And so I'll get the affine patch of the toric variety I care about. The toric variety with fan is made of the Neff cones. So at least the base is correct. I should consider an algebra over this ring, C double bracket any of x. And as a module over this algebra, I have a basis theta p, where p are integral points in the cone over the dual complex of this semi-stable degeneration. So there is a dual complex which encodes the combinatorics of the central fiber of this degeneration. And the integral points of this dual complex naturally index the basis of this module. And the whole issue is to put an algebra structure on this module to say what theta p times theta q here is. And it is here that there is something extremely non-trivial going on. The product is defined, so the structure constant of the product with respect to this basis is defined using enumerative geometry, using a version of what is called logarithmic Gromov-Wheeler invariance, which have been developed by Abramowitsch and Gross and Siebert, and which is an extension of usual Gromov-Wheeler theory, which has to do with counting curves in algebraic varieties. And here it's logged because we want to impose the tangency conditions for our curves relatively to the normal crossing central fiber in this degeneration. So here there is something extremely non-trivial going on. There is some enumerative geometry, some Gromov-Wheeler theory. And the main result of Gross and Siebert is that if you define your structure constant using this kind of curves, you indeed define some associative commutative graded algebra. And if you take proj of that, you get some geometry. Okay, so this may be here the most non-trivial aspect of mirror symmetry. That mirror symmetry predicts a way to construct some algebraic geometry, which in a way which is maybe not classical. You start with some geometry, you do some curve counting in this geometry, and somehow you can arrange this curve counting as structure constants of a ring. And if you take proj of this ring, you get a mirror geometry. And so we apply this general construction to a particular situation. There are a lot of technical issues. So in general, when you apply this construction, you have to deal with generating series of these curve counts. So you only produce in general some kind of formal objects. And here we prove that in our setup, actually, you don't get a formal object, but you get some honest algebraic variety over the affine toric variety spec C any x. So for any Crépin resolution x of x bar, you produce some family over spec C any x. And not only you can produce a family of varieties, but there is a natural way to cook up a line bundle on it. And there is a natural way to cook up some divisor on it. So actually what you can cook up is a family of pairs yd plus epsilon c over these various affine toric varieties spec C any x. And actually when you vary x among the possible Crépin resolutions of x bar, you can glue all these families together to get a single big family of pairs over the toric variety with fan given by the Mori fan. And the final step is to show that whatever we just constructed, this family of pairs, actually is the thing we started with, that these pairs are in the same deformation class as the original pairs we're looking at. And if it's true, then it means that there is a classifying map from this toric variety to the Moduli space we care about. And so this thing is another main result, which is that whatever we construct is a family of KSBA stable log Calabi-Yau surfaces with general fiber deformation equivalent to the original pair YDL. So here there is something quite non-trivial going on, because if I come back to this diagram, the diagram here, I'll start with YDL. Then I do some deformation theory argument to produce a mirror. And then I do some curve counting in the mirror to cook up some kind of abstract ring. And I take project of this ring, and somehow I'm supposed to recognize what this ring is. I'm supposed to recognize that this variety I construct actually is related to the original variety. So in other words, it's a general expectation that mirror symmetry should be some kind of involution. The mirror of the mirror should be the original geometry. But actually, in most cases, with most known construction, actually this property is highly non-trivial and highly mysterious. And so here, what we need to do is to establish one case of this kind of involution of mirror symmetry. One is to prove that starting with some geometry, we apply some kind of mirror construction. We apply some kind of mirror construction back. Why do we come back to the original point? And to do that, we use the fact that we're in dimension 2. We can have some kind of relatively explicit understanding of the topology and geometry to be able to do this identification of what happens when you do mirror symmetry twice. And not only you need to show that you come back to your original geometry, but you also need to prove that whatever geometry you produce satisfies the KSBA stability condition. You should need to check that whatever you produce has similar canonical singularities. And it is actually where most of the technical work is lying. And so finally, once you produce this family over this candidate toric variety, then by universal property of the Moduli space, you get a map from this toric variety to the Moduli space you care about. And the final things to establish is that this map is, first of all, surjective. We did not produce a trivial family, but we really produced a universal family. And actually, this map is finite. And so each of these statements requires a non-trivial argument that I will skip. And here, just as an illustration, I have written down something which is like a really toy model, maybe too simple, but still you could try to understand what happens in this situation. If you start with a pair which is P2 with a line union a conic, and if you take your line bundle to be just O of 1, so which means the extra divisor I was drawing in red before is a line, then in this case, you can check the corresponding KSBA Moduli space is indeed toric, actually just P1. So here, the picture of the general element in the Moduli space is this red line, which is like a general line with respect to the fixed line and conic. And then at one point of this P1, the line and conic degenerate to a triangular line. And at the other line, there is something special which happens. Actually, I've forgotten what happens. What happens exactly that this configuration gets some extra automorphism group, an extra finite symmetry group. So in this very simple example, if you want, it's an exercise to figure out explicitly what the geometry is. But the point is that you can check what is a mirror interpretation of this fund. So you could interpret this fund in a mirror way. It's a nice exercise to do. Okay, so my time is over, so I will stop there. Thank you for your attention.
Thank you so much. Any questions?
So can you elaborate a little bit on this polytope that you maybe skipped a little bit earlier?
About which
In the
part?
non-toric situation.
Yes.
So what is this polytope in
Oh,
general?
yeah, that's right. So let me mention that. So it's something I did not really mention. So if you're in the toric situation, for a polarized toric variety, there is a polytope. If I have a non-toric log Calabi-Yau pair, so actually in general, in any dimension, I don't know what to do. But if you're in dimension 2, there is a toric model, which means roughly your geometry can be obtained by a blow-up of something toric. So you can start with a polygon of the toric geometry. And then you do some blow-up of points on the boundary of this toric surface. And then your line bundle L will be pullback of a toric line bundle plus a multiple of the exceptional divisors. And using this information, you can cook up what is something called a Symington polytope. So here at the bottom of this picture, I have a triangle with a decomposition. And I have a particular white triangle. And the data of this triangle is determined by the data of the particular line bundle I'm choosing. And out of this polygon, which is a toric story, I can cut out this white triangle and then identify the remaining side of the pink picture. And if I do that, I will produce some integral affine manifold with singularity, having a singularity at this red point. So in this non-toric situation, if I make a choice of a toric model, I can still cook up some version of the polygon, but it will be some Symington polygon, some polygon with some integral affine structure with integral singularities. And out of this data, I can use this data to cook up the mirror geometry. Essentially, I want to interpret this integral affine manifold as a dual complex of the mirror geometry. And I cook up my mirror geometry in such a way that it can be done.
I see. So for instance, here are some of my follow-up questions. So for instance, so I guess this polytope should somehow, like in the toric situation, if you have two different line bundles, then the corresponding polytope to be maybe preserved under Minkowski sum when you add the line bundle, something like this. But is that easy to see from the picture?
Yeah, I don't remember. Yeah, it's very likely there is a relation of this sum. That's true.
And maybe a different question is like uh so I guess in general, one way to attach a convex body to a line bundle is like this Okhunov body. But is there some kind of relation in this direction?
Yeah, so I think, okay, let me see. Yeah, definitely at some point we thought about that. And I think the short answer is I don't really know how to do that directly. So yeah, I don't know. Yeah, in particular, it's related to the fact that this polytope, actually, if you do this Okounkov body, you will get an honest polytope, right? Whereas here, I'm not getting an honest polytope, I'm getting these kind of integral affine structures. So of course, sometimes they are related, but
Yeah, because at the end you mentioned that the lattice point in this polytope somehow parameterize or give you a basis
that's
of the
right.
sections.
Yeah, that's right. So what happens, okay, let me try to get it right, is that our log Calabi-Yau geometries sometimes admit degeneration to toric geometries. Like maybe the pair YD plus epsilon C, sometimes there will be degeneration whose central fiber is toric. And then it is in this context that what will appear will be something like a Okounkov body. and some kind of polygon describing this toric limit of our non-toric things. So definitely they do appear somewhere in the story, but they are not on the nose the same thing as a polytop we consider.
I see. Good. Yeah. Thank you.
I also have a question. And so you say that you are getting a finite covering of that space.
Yeah.
And so you're parameterizing not a local Calabi-Yau surface plus some additional data. Do you know what is additional data?
Yeah, so when we wrote our paper, we didn't know, but we're currently writing a follow-up paper which will fully explain what happens. And actually, I think for someone familiar with like moduli of K3 surfaces, it will not be surprising. So the extra data will be some kind of marking of the cohomology. So yeah, so let me see. So if you look at the pair YDL, maybe let's assume for simplicity y is smooth. Then I have H2 of y, which is a cohomology of y. And I can consider in H2 of y the classes which are orthogonal to all components of D and also orthogonal to L. And by the Hodge index theorem, this lattice will be like negative definite. And essentially, I want to fix a marking of this lattice. So the finite group will be roughly at least will be contained in the orthogonal group of this definite negative lattice, which is one of the reasons why it is finite. It's because in this story, there's a natural lattice. Essentially, the orthogonal to the line bundle and to the divisor D. And it's this kind of maximal log Calabi-Yau situations, this lattice is definite, which is why you get a finite group. So if you do the traditional story, for example, for K3, people look at the orthogonal of L, but then the lattice is still indefinite, which is why you only get something like toroidal, like after, I mean, you get some kind of orthogonal group, which is like infinite. Whereas in this kind of maximal log Calabi-Yau situation, there is a kind of analog story, but which is much simpler. There is a marking of this lattice, and this lattice is definite, so the kind of ambiguity of this marking will be a finite group. And we claim that it is exactly the ambiguity which appears in our theorem.
I see. And so this has something to do with the work of Jennifer Lee, or?
Yeah. Yeah, so actually, I'm not sure. Is it they work on like Modi space of log Calabi-Yaus in general?
Yeah.
So my understanding is that they consider something different. So they really consider a variety with an anti-canonical divisor, and this thing is a pair.
Yes.
Here we consider D plus epsilon times. So I think the precise type of pairs we consider are actually different.
Yeah.
And
we also have an ample.
and so I think I do not understand if there is a natural intersection between these stories.
Okay, thank you.
Thank you. These are all very good questions.
Other questions or comments? If not, thanks again.
Yes, thank you very much.